stole my whole introduction. So now it's going to be a repeat of everything you just said. But hello and welcome to Team Mega's Senior Thesis presentation. We want to thank you all for coming to support the last 3 years of our research and the culmination of research and smelly fish tanks. Team Mega stands for maximizing the efficiency of greenhouses using aquaponics. Our team consists of 14 members, you can see in front of you: Adam, Alan, Austin, Jonathan, Kaliani, Callie, Kevin, Miriam, Lauren, and Winston. I am Daniel, and presenting with me today will be Jessica, Luke, and Eric. And our mentor, wonderful help, is Dr. Andrew Lazar from the College of Agriculture and Natural Sciences. We will begin today's presentation with a brief overview of the current research on the problem and what we got from that. We will then continue with our 4-phase experiment and how it relates to our overall research question. We will then finish with the conclusion of our work and the future work related to it. And with that, our research started with a well-known problem. 1 person out of every 8 people in the world does not have enough teeth. Further, some of the current food production techniques are unsustainable, leading to significant harm to the world's ecosystems. For example, overfishing has reduced the world's large fish population by 90%, in particular with fish like tuna and swordfish. Due to market demands, selective fishing has resulted in smaller fish and slower growth. Because of this, wild-caught fish are unlikely to satisfy our current or future protein demands. Also, the food production system of the United States is very energy intensive, consuming 17% of the United States' energy. Agriculture is the single largest consumer of petroleum products when compared to any other industry. Finally, rural areas are faced with problems in food allocation. Due to reduced arable land and climate change, these areas are not able to produce enough food. Also, these areas have problems with reliable electricity and market access, which makes it more difficult to implement the current food production techniques in these regions. For these reasons, our team's research looked at aquaponics. Aquaponics is a combination of aquaculture and hydroponics. Aquaculture is the practice of raising fish, while hydroponics is the practice of growing plants without soil. Put the two together and you have fish and plants working in a symbiotic relationship. In particular, we had a recirculating aquaponics system, meaning the wastewater from the fish was pumped up to the plant beds, where it not only fertilized the plants, but also was filtered before it flowed back down to the fish. This meant that the water was reused, which is ideal for developing areas with limited water. Also, this means that the plants do not need any supplemental feeds, and the only 2 inputs to the system are fish feed and sunlight. Aquaponics is not a new idea, but it has been increasing in popularity in recent years. One of the most documented systems was developed at the University of the Virgin Islands in the late 1990s. This system raised tilapia because of their efficiency at converting fish feed to body mass. But because this system relied on high energy and expensive feeds, it is not suitable for developing regions. Because of this, our team's research focused on developing a similar system, but one that could be used in developing areas, in particular in rural areas. We wanted our system to be subsistence level, meaning it would feed the family that wanted it. As I mentioned, aquaponics, as it currently stands, is not a solution to the world hunger problem. Aquaponics relies on commercial fish feed, which is heavily comprised of fish meal. Fish meal is basically ground up bits of little and inedible fish. And the demand for fish meal has resulted in further overfishing of the world's oceans. In this graph, I hope you guys can see from back there, we see the price of fish meal from 2005 to 2012. And you can see the price increasing steadily as demand increased. One alternative to this problem is alternative plant-based feed sources. For example, soy meal, also shown in this graph, has not shown a significant increase in price over these last years. Although there has been research done in this field, there is not enough done in particular with respect to aquaponics. For this reason, our research question asked, what alternative feed sources can effectively and efficiently support a subsistence-level aquaponics system? We hypothesized that by using alternative feeds, we could produce comparable yields to a system which uses commercial fish feeds. At the same time, these feeds would be cheaper in developing regions and would reduce costs, resulting in an overall more efficient and effective aquaponics system. And to give you an idea of how we went about doing this, I'm going to go over the 4 phases of our research. We will then present each of them in more detail. In phase 1, we grew duckweed, and we grew this with 4 alternative nutrient sources. Using the results of phase 1, we were able to determine the best alternative nutrient source for duckweed. Duckweed would then be used 2 and 3, where it will be compared alongside 3 other nutrient sources and a control of commercial fish feed in a small-scale aquaponics system. This aquaponics system would raise the line. Phase 3 was similar to Phase 2, except the commercial fish feed was blended with alternative nutrient sources for the reasons which we'll explain later. In Phase 4, we constructed a large-scale aquaponics system that would more closely resemble our target application. In this system, we compared the best alternative fish feed from the previous phases against the control of commercial fish feed to determine whether we could use this alternative fish feed as a suitable replacement. With that, I'm going to go on to Phase 1. In Phase 1, as I mentioned, we grew duckweed. Duckweed is an aquatic plant that has been shown success as a fish feed. Not only is it common and fast growing, it grows with a variety of nutrient sources, making it ideal for developing regions. Duckweed can be used as an intermediary with waste nutrient sources, such as compost. In this case, the compost would be used to fertilize duckweed, which would then in turn be used to feed the fish. In Phase 1, we looked at 4 waste nutrient sources: activated sewage sludge, dairy manure, vegetable compost, and poultry manure. In this 2-week experiment, we aimed to identify the best alternative nutrient source to fertilize duckweed. Each of the 4 alternative nutrient sources were compared against the control of no fertilizer, and each treatment was conducted in triplicate for a total of 15 tanks. In Phase 1, daily fertilizer amounts were standardized by nitrogen content. Every 2 days, we harvested half of the surface area of the duckweed tank and dried and weighed these harvests. With this, we were able to measure the total biomass produced by each treatment, and were able to then conduct laboratory analysis to determine the protein content. With the protein content and the biomass, we were able to get the total protein produced by each treatment. This graph shows the results of our Phase 1 experiment. On the y-axis, you can see total protein produced, which, as I mentioned, was a product of biomass and protein content. And you can see on the x-axis are 5 treatments, starting with control. The error bars in this experiment represent standard deviation, and the bars at the top of the graph indicate significance as determined by a one-way ANOVA test. In particular, you can see that activated sludge had the highest total protein produced, and was significantly different than control, vegetable compost, dairy manure. However, it was not significantly different than poultry manure. Regardless, we chose activated sewage sludge as the best alternative nutrient source to fertilize duckweed. With this, activated sewage sludge was chosen to continue on for the remainder of the experiments and was used as a fertilizer for duckweed for Phases 2 and 3. And I'll turn over to Jessica to present that phase.
Thanks, Dan. In Phase 2 of our research, we constructed 10 small-scale aquaponic systems of our own design. 9 tilapia were reared in 55-gallon holding tanks below the surface of the table, while plants were grown overhead in floating polystyrene racks. In aquaponics, the only input needed is fish feed, which will sustain the entire system due to the recirculation of water and nutrients to the plants above. Phase 2 was an 11-week study aiming to identify the best alternative feed source that can be used in small-scale aquaponic systems. In this phase, we use 100% feed replacement diets. All of these experiments took place in controlled growth chambers, where parameters such as lighting, temperature, and humidity were closely monitored and controlled. All of our treatments were tested in duplicate. The alternative feeds we tested in Phase 2 included rice bran, soybean meal, soba, and duckweed that was fertilized with activated sludge, as determined by our Phase 1 system. All of these alternative feeds were tested against a control of commercial fishing. Here are some pictures of our Phase 2 setup. The species we used included Nile tilapia, bib lettuce, and Genovese basil, which we determined to be suitable species due to their use in aquaponic systems, as seen in the existing literature. So our Phase 2 protocol included regular water chemistry tests to ensure satisfactory living conditions for our fish. We also weighed the plants on a weekly basis in order to adjust their feeding quantities based on their growing body mass. We also harvested the edible plant matter on a weekly basis to measure overall plant production over time. All of our alternative feeds were pelletized to ensure equal palatability for the fish. And so here are some pictures of animation displaying our plant growth over a period of 3 weeks. As you can see, the plants really flourish in our aquaponic system. Water chemistry was assessed on a regular basis to ensure water quality as well as fish health. By far, nitrate compounds such as ammonia, nitrite, and nitrate have the biggest effect on fish health. This is because in aquaponics, fish excrete ammonia as a waste product, which is then converted to nitrite, then nitrate through the nitrogen cycle. Plants then take up this nitrate, thereby filtering out the water environment for the fish. High levels of ammonia and nitrite can be toxic and detrimental to fish health. Thus, it was very important that we measure these parameters and kept a close eye. So here are the results from our phase 2 study. On the x-axis, we have all of our feed sources, while on the y-axis, we calculated the growth percentage per tank, which was calculated by dividing the change in mass by the initial mass. A one-way ANOVA determined that there were significant differences in fish growth between control and all of our alternative treatments, indicating that in terms of fish growth, they were not comparable to a diet of commercial fish. However, we did see some success in our plant production. On the x-axis, again, we have our feed sources, and on the y-axis, we have total plant biomass in grams. A two-way ANOVA determined that there was no significant difference between our control treatment when compared to duckweed and soybean meal, suggesting that they were comparable, suggesting that duckweed and soybean meal were comparable to commercial fish feed. Because we saw poor tilapia growth in our phase 2 system, we had to narrow down our alternative feeds based on plant production alone. And thus, we determined that duckweed and soybean meal are the two best alternative feeds that will move on to the next phase of our research. Initially, we wanted to conduct a second small-scale growth cycle using 100% feed replacement diets in order to ensure the replicability of our protocol. However, because we saw poor fish growth, we decided to shift our focus to a 50% alternative, 50% commercial fish feed diet. We anticipated that by using this substitution, we would still reduce costs and improve the sustainability of our feeds while hopefully seeing better fish growth. And thus, we moved on to phase 3 of our research, which was an 8-week study aiming to identify differences between duckweed and soybean meal, which were the two best alternative feeds as determined by phase 2. This time, the treatments were presented in a 50-50 blended treatment. The experiments took place in controlled growth environments once again, and the protocols remained the same as that of phase 2, which included weekly fish weighing, plant harvesting, and water treatments. This time, all of our treatments were tested in triplicate. So here are the results from our phase 3 study. On the x-axis, we have our feed sources, while on the y-axis, we have growth percentage. Unfortunately, we saw a high number of fish deaths in phase 3 due to an unknown pathogen, and so growth percentages were calculated via individual fish rather than entire tanks, as they were in phase 2. As you can see, a one-way ANOVA test indicated that there were no significant differences in fish growth between control and our two alternative treatments, both duckweed and soybean meal, indicating that in terms of fish growth, our alternative treatments were comparable to that of the commercial fish feed diet. We did see significance between our two alternative feeds, either soybean meal and duckweed, suggesting that soybean meal was the better alternative. In terms of plant production, we saw no significant differences between any of our treatments. Therefore, we could make no conclusive statements about the effectiveness of our alternative feeds based on plant growth. We anticipated that the best alternative feed would produce the highest fish growth as well as the highest plant weight. Overall, in phase 3, plant weight was ultimately consistent. However, fish reared on a soybean meal blended treatment grew significantly better than fish grown on a duckweed blended treatment. Although confounding variables such as the fish deaths may have influenced the results of our study, we still found that soybean meal was the best alternative feed that would move on to phase 4 of our research, which was a large-scale application of our aquaponic system. And now I will turn it over to Luke, who will discuss our phase 4 study.
Okay, thank you, Jessica. So as Jessica had mentioned, our phase 4 methodology was we wanted to investigate the effectiveness and the economic feasibility of using soybean meal blend in a larger scale aquaponic
aquaponics system. The 9-week study had consisted of soybean meal blend and control treatments conducted in treatment. This was a more real-world application compared to the highly controlled environment of the growth chambers in phases 2 and 3. Unpredictable weather conditions such as wind, temperature fluctuation, and humidity now became a factor. However, we kept our procedures for harvesting and water chemistry consistent. This study was conducted in Hightown on campus. We had 6 subsistence level aquaponic systems. Each system consisted of a 200-gallon fish tank and a 3.7 square meter plant bed. In addition to the larger scale systems, we implemented other components to allow for optimal growth. Because phase 4 was conducted in the late fall season, we implemented heaters to control water temperature. A water pump was implemented to create a 500-gallon per hour flow rate. Plants were grown in PVC pipes to allow roots easy access to water and nutrients. Before the water flew back into the fish tanks, we had biomedia tanks for filtration. Here are our results for fish growth percentage. Again, on the x-axis, we have our feed source, and we have our growth percentages, which was the change in mass divided by the initial mass. As you can see, the control tank had 700% increase in growth, while the soybean meal blend only had a 480% growth percentage. And one way ANOVA concluded that there was a significant difference between these two feeds, meaning that our soybean meal blend in terms of fish production was not a comparable feed source. Here are our results for plant production. You can see here again we have feed source on the x-axis, and on the y-axis we have plant biomass. We did not find any significant difference between these feeds for plant production, meaning that soybean meal is a comparable solution in terms of for plant production. However, due to high standard deviations and we didn't see much plant yield, we're hesitant to accept these results. So to recap, we found a statistical difference in our fish production, but not in plant production. So we can't say that soybean meal blend is comparable, but the growth did reveal that it is a viable supplement for commercial fish feed. After our growth trials were concluded, we continued with a cost savings analysis here. As Dan previously mentioned, the fish meal is one of the most costly and unsustainable ingredients in commercial fish feeds because of its increased pressure on wild-caught fish feeds. So we utilized the International Monetary Fund's Commodity Price Index to investigate the economic advantages of utilizing alternative nutrient sources. As you can see here, soybean meal is 1/3 the cost per metric ton of fish meal, which reveals that there's automatic economic advantages for using alternative feeds. We continued our economic analysis by extrapolating data from our experimental system. We utilized our feed conversion rates and estimated close to a 9% cost savings by switching to a 50-50 blend versus commercial fish feed. We wanted to see how this economic advantage could be utilized in a real case study. So we found this case study from Bangladesh where farmers were formulating their own feeds with plant supplements. They had 10% of their feed was fish meal, but it was 45% of their overall cost. So if they had utilized only 5% fish meal and substituted 5% soybean meal, they could have seen a 22% cost savings. And so this case study is an example of the economic applicability of using substitutions for commercial fish. I'll now turn it over to Eric, who will discuss our future directions and conclusion.
Thanks, Luke. That's not too loud. Good. All right. Looking forward to implementation, there are a number of considerations for the design of an ideal subsistence-level aquaponics system for use in a wide range of developing countries. High capital requirements are probably the single greatest obstacle to the expansion of aquaponics, and therefore reducing them will open further opportunities for funding and allow a faster, more widespread implementation. The system needs to be built from commonly available materials. These materials should be nearly ubiquitous, otherwise the system will have limited applicability. Similar to the construction materials, the feeds used in the system need to be readily available from a reliable source. Our project primarily focused on this aspect, though we did consider the other facets throughout the project as well. Many of the regions that we're considering for implementation do not have a reliable supply of electricity. To work around this challenge, an ideal system would have low energy requirements, as well as incorporating some form of energy storage or generation. It's not feasible for a small-scale system like this to have advanced monitoring and controls. Therefore, the system needs to be robust enough to handle swings in temperature, humidity, light levels, and other parameters without failure. Team Mega found that soybean meal is a viable alternative feed for tilapia and aquaponic systems. That said, further work is still needed in order to expand our knowledge of complete feed formulations from a variety of feed components. These feeds could be blended locally and adjust to current supplies of ingredients, giving them an immediate advantage over commercial fish feeds. Duckweed, our second best alternative feed, is of particular interest as it could be grown using wastewater, providing an inexpensive means of wastewater treatment, as well as reducing feed costs. As I mentioned, the construction materials need to be readily available and inexpensive. Fortunately, there are a number of ways to build the components of an aquaponic system. The fish tanks, for example, can be grown by stacking cinder blocks and inserting a pond liner. The plant beds can be made by cutting plastic barrels in half and inserting either floating rafts or a solid media substrate like gravel to allow the plants to root. To reduce energy use and therefore operating costs and reliance on local, often questionable infrastructure, we considered a number of possible innovative solutions. In aquaponics, a majority of the energy used is for water circulation. This provides oxygenation, filtration, and keeps waste in the water column so that it can be removed. Instead of constantly running an electric pump, one could use a bicycle-powered pump or a bucket to move water to an elevated water storage tank. The water could then flow slowly through a valve into the plant beds, providing nutrients, and then into the fish tank, providing oxygenation. In this way, the system can be maintained during power outages. Our intended application is in tropical regions for two reasons. One, a majority of the developing countries, and particularly those with the greatest food security challenges, lie in the tropics. And two, our study species tilapia cannot tolerate cold temperatures. To actually implement a system like this, we would look to funding methods that have been used by similar projects like no-interest loans and microlending. We envision the system being used by a family or small community to grow staple food crops for their own consumption, as well as cash crops that they can take to market to provide an income. To give you an idea of the production of the system of this design, we used our own findings as well as existing literature to project the yield of a system using two 1,000-liter fish tanks and a 75 square meter plant bed with alternative fish feeds. We found that the yields would be over 1,200 kilograms of tilapia, 9,000 heads of lettuce, and 600 kilograms of basil each year. Now obviously you wouldn't eat 9,000 heads of lettuce in a year, but you could substitute other kinds of crops as well. So for a system cost of under $5,000 and a feed cost of under $600 a year, you could gross over $35,000 in fish and produce each year. Now this analysis doesn't take into account the cost of labor or differences between markets, but it still gives you a general idea of the production of a system like this. So, in summary, in phase one, we learned that duckweed is a potential low-cost feed that can also provide inexpensive wastewater treatment. And in phases 2, 3, and 4, we identified soybean meal as a viable alternative feed for tilapia and aquaponics diets, which would reduce feed costs as well as reduce reliance on the local wild fish stock, making aquaponics a viable solution for reducing global food insecurity. Over the course of the project, we've been very fortunate and have received generous support from a wide number of people. However, we would be remiss if we didn't thank our mentor, Dr. Lazar, first and foremost. Without him, we simply could not have come this far. We'd also like to thank the Gemstone Program, our librarian, Nevenka, UMD Sustainability Council for their money, all of our discussants for coming and providing feedback. And with that, I'd like to thank you all for listening, and we'd love to answer any of your questions.
So we're going to take 10 minutes of questions from the discussants first, and then we're going to open up the floor to general questions.
All right, well, first of all, congratulations on a very nice and professional presentation, and congratulations on a research project. Clearly, from having read your paper, was a very clear, logical journey from an initial idea to a finished product, so you should feel very good about that. So that's the nice part over. Now let's go to the questions. You had 4 phases of the experiment. And I'm going to focus on phase 3 and 4, where the results were somewhat different. What do you learn from the differences in those results? How do you explain the differences? I mean, you had soybeans growing higher plants in phase 3, but less in phase 4. You had equal fish production in phase 3, but improved fish production on soybean in phase 3, but reduced fish production in phase 4. What do you take from those differences about the reliability of the system and the reliability of your inferences?
Thank you for the question. The question was, what differences and what conclusions can we make from those differences in phase 3 and 4, especially with respect to soybean meal growth, which was not drastically, considerably different between the 2 phases.
So the main difference between our phase 3 and phase 4 studies is definitely the environment in which they were conducted. In phase 4, we had to deal with a bunch of extraneous factors that we weren't expecting that we did not experience in phase 3, where parameters such as humidity and temperature were very closely controlled. And so in phase 4, we not only exhibited drastic temperature spikes where the plants bolted at a certain point because of extreme high temperatures within the greenhouse, we also experienced a very drastic temperature drops towards the end of our growth season, around mid-October. So we definitely attribute those to the inconsistencies in the results.
Another potential influence on that is the fact that in phase 3 we did experience a lot more fish deaths. In phase 4 we had over 98% survival. In phase 3 it was much lower, so that could have definitely reduced the reliability of the results in terms of fish production. Fish deaths was a lot better.
Like Tom said, you guys did a great job. Thank you for having me here. I really enjoyed reading through your thesis, and so yeah, like Tom said, let's do some hard questioning. As far as nutrient density, you introduced the paper talking about malnourishment, hunger, food security, and this being a solution, which it definitely will be. But how does you guys analyze growth and weight, biomass, the plants, and the fish weight, but what role did nutrient density play in your analysis, in your thought process about this? Because, for example, Purdue is one famous company, not too far away. They make these really big chickens. You get to the farmer's market and you buy pastured chicken, different type of growth and environment. And you find that they're leaner and they're smaller, but the flavor changes and the nutrient content also change. And there's a debate over, is it just about weight yield? So how did that play a role in your thought process, and how would that affect future analyses and experiments about this?
Thank you for the question. So just to summarize, I think you did a very good job of explaining the question, but how did nutrients and kind of quality of the produce affects the results and also the questions that we looked at in our experiments. I think we can answer those.
Thank you for your question. So we did not have the funding to do a nutrition analysis after each phase, but after our phase 2 results, we did send off a few fish samples to the lab to test for nutrients, toxins, make sure there weren't high levels of metals, things like that. So yes, we did take it into account, but it wasn't the main focus due to funding. And I forget, we had very low levels of toxins, appropriate levels, and so we did take it into account.
And we haven't done it yet. We're planning on doing a flavor analysis just within the group. Coming out on our fish that we actually shot.
And so I can't really build off of that same train of thought right now. That a different type of system and a different type of application to lend itself to a different type of growth. Considering that the primary goal of this is to develop a concept that you can use for a family to feed themselves, you would need breeding of those fish to sustain the population. And to do any investigation or reflecting out whether or not this type of system is appropriate for using the broodstock or spawn at some time. I know you didn't try one spawn. How well was that considered as part of the project?
The question was, how is breeding and the breeding stock affect, how would it affect our system, and what considerations do we take in order to mitigate any problems with that?
Let everybody jump in.
Yeah. So we did use an all-male population for this research just reducing value variables. It's very standard practice. But as far as tilapia go, it is fairly easy to get them to reproduce in captivity at a rate where you could keep a brood stock in one system and pretty much be self-sustaining